The Japan-Korea undersea tunnel has been proposed for over a century, but the consensus among every official feasibility study is that it remains economically impossible. The Korea Transport Institute estimated the combined construction cost at 100 trillion won, roughly $90 billion, with a benefit-to-cost ratio so low that no government has formally committed. And yet, in 2025, a consortium of Japanese engineering firms quietly filed a new technical proposal that claims to cut that price by nearly 40%. Here is what nobody tells you about building a tunnel through an active tectonic subduction zone, where the seabed drops 100 meters every 20 kilometers. You are looking at a map of the Korea Strait, and you think you understand the scale. 128 kilometers at the shortest straight-line distance between Kyushu and Busan. That is roughly the same as the English Channel Tunnel, but with one critical difference. The Channel Tunnel sits in stable Cretaceous chalk. The Korea Strait sits directly above the Philippine Sea Plate, diving under the Eurasian Plate at a rate of 4 centimeters per year. That means the ground you are drilling through is not static. It is moving, it is fracturing, and it is generating earthquakes that can exceed magnitude 7 every 40 to 50 years. The first thing you need to understand is that a tunnel boring machine cannot simply chew through this material the way it does through clay or limestone. The rock under the Korea Strait is a mosaic of welded tuff, andesite, and sedimentary layers that have been folded and faulted by millions of years of compression. At the depths required to avoid shipping traffic and seismic surface rupture, the cutter head will encounter rock with compressive strengths exceeding 200 megapascals. That is harder than the granite that slowed the Gotthard Base Tunnel for years, and the machines that could handle it cost upwards of $50 million each. You will need at least 4 of them working from both sides simultaneously to meet the 15-year timeline. Now, consider the water pressure. At a depth of 200 meters below sea level, which is the minimum for a tunnel of this length to maintain a safe gradient, the hydrostatic pressure exceeds 20 atmospheres. Every square meter of tunnel lining will feel 200 tons of force pushing inward. If that lining has a crack just 2 millimeters wide, water will jet through at velocities capable of cutting steel. The ITA collapse report from the 2022 case study documents exactly that failure mode in a much shallower undersea tunnel in Norway. The only difference was the water depth. The same crack at 200 meters would flood the tunnel in under 4 minutes. The engineering community is divided on whether you can even seal a tunnel in this environment with conventional gaskets. The standard solution is a compressed graphite ring that expands when it contacts water, but those rings are rated for pressures up to 60 atmospheres. At the Korea Strait, the combined hydrostatic and tectonic loading could exceed 80 atmospheres during a seismic event. Graphite doesn't fail immediately. It creeps. Over 10 years, the seal deforms by a millimeter. Over 20 by 3. And 3 millimeters is exactly the margin that separates a watertight tunnel from a catastrophic leak. That 3 millimeter margin is everything. It is the gap that kills a tunnel before it pays back its debt. If you want to see what other failure modes never make the press releases, subscribe. This channel exists because the details that break projects are buried where the cameras never go. In the comments, write creep, one word for the failure mode that no one budgets for. So the question becomes not whether Japan can build this tunnel, but whether it can stay dry long enough to pay back its construction cost. The Japanese consortium's new proposal avoids this problem by changing the fundamental geometry. Instead of a single deep tunnel, they propose a series of shorter sections connected by artificial islands at Iki and Tsushima. The depth decreases, the water pressure drops, and the tunnel boring machines never operate below 100 meters. That changes everything about the gasket design, the ventilation system, and the emergency evacuation routes. But it introduces an entirely new set of problems that most engineers have not yet begun to solve. The artificial islands themselves would require dredging and piling in waters that experience typhoon surge, waves up to 12 meters high. The 2023 storm season in the Korea Strait produced wave heights that damaged a South Korean research platform designed for deep-sea oil exploration. That platform was built to survive waves of 15 meters. It lost its helipad in a storm that the meteorological agency called a 1-in-50-year event. The tunnel islands need to withstand the same conditions, while also supporting the weight of tunnel-boring machine launch structures, ventilation shafts, and a permanent staff of at least 50 engineers during operation. The cost of those islands alone is estimated at 2 trillion yen, roughly $18 billion. And that is before you dig the first meter of tunnel. The Japanese consortium argues that this is still cheaper than a single deep tunnel because it halves the number of gasket replacements over the structure's 100-year design life. But there is another number that keeps the feasibility studies from moving forward. The Korea Transport Institute found that even at the most optimistic traffic projections, the tunnel would carry fewer than 30 million passengers per year. The Channel Tunnel carries nearly 21 million and still struggles to break even on its debt service. A tunnel between Japan and Korea would need to generate revenue from both passenger rail and freight to have any chance at viability. The freight projection is where the numbers get interesting. The current shipping route between Busan and Shimonoseki handles approximately 40 million tons of cargo annually, moving through some of the most congested shipping lanes in the world. A rail tunnel could divert about 15% of that volume, saving an average of 3 days in transit time per container. But the tunnel would need to charge tolls competitive with sea freight, which currently runs at roughly $50 per ton. The rail operating cost alone, including ventilation, pumping, and track maintenance, is estimated at $32 per ton. That leaves a margin of $18 per ton to pay off a $90 billion construction loan. At 15 million tons per year, that margin generates $270 million annually. The loan payment on $90 billion at 3% interest is $2.7 billion per year. The math does not work, and yet the consortium continues to file proposals. The reason is not economic, it is strategic. The Korea Strait is the narrowest choke point between the Sea of Japan and the East China Sea. A tunnel that connects Japan to the Asian mainland rail network would bypass the sea lanes that currently carry 60% of Japanese imports. The Japanese government views this tunnel not as a transportation project, but as a supply chain insurance policy. The same logic drove the construction of the Seikan Tunnel, which connects Honshu to Hokkaido through a sub-sea section that reaches depths of 240 meters. That tunnel cost 700 billion yen and took 17 years to build. It operates at a loss, but it ensures that Hokkaido remains connected to the national rail grid, regardless of weather conditions in the Tsugaru Strait. The Seikan Tunnel is the closest existing analog to the Japan-Korea proposal, and its engineering failures tell you everything you need to know about why the new tunnel is so difficult. The Seikan encountered unexpected volcanic rock that caused the tunnel boring machine to seize up for 6 months. The water inflow was so severe that the contractor had to freeze the ground using liquid nitrogen to stop the flow. That technique had never been attempted at that scale, and it added 2 years to the construction schedule. The Korean Strait geology is significantly more complex, with multiple fault lines that have not been fully mapped below the seabed. The 2011 Tohoku earthquake shifted the seafloor near the Japan Trench by 24 meters horizontally and 3 meters vertically. That is a single event. The Korea Strait accumulates that much tectonic strain every few centuries, but it releases it in smaller, more frequent events. A tunnel that survives a magnitude 6 earthquake might not survive the creeping deformation that follows. The gaskets could hold during the shaking, but the alignment of the tunnel segments could shift by centimeters, changing the load distribution across the entire structure. No simulator has reliably modeled that scenario because the variables are too numerous. That is exactly the kind of problem that separates a real tunnel from a proposal. If you want to stay with the engineers who are trying to model the unmapped variables, subscribe. This is the infrastructure story that no journalist touches because it is too technical. In the comments, write unmapped. Tell us about a project where the ground surprised you in a way no simulator had predicted. This is the part that the press releases do not mention. The Japanese consortium's proposal includes a plan to monitor the tunnel's structural health using fiber optic sensing cables embedded in the concrete lining. Those cables can detect strain changes as small as 1 microstrain, roughly the equivalent of a single sheet of paper resting on a kilometer of steel. But the data from those cables would need to be processed in real time, and the threshold for human action has never been defined. At what microstrain do you evacuate a tunnel that is 100 kilometers long? How do you evacuate when the nearest emergency exit is 15 kilometers away? The Seikan Tunnel solved this problem by building a service tunnel that doubles as an escape route. The Japan-Korea proposal cannot afford that luxury. The cost of a parallel service tunnel would add another $30 billion to the budget. The answer, according to the consortium's lead engineer, is to design the main tunnel itself as the escape route. Every section would be pressurized slightly above atmospheric, so that a breach would cause air to flow outward, rather than water inward. That system works on paper, but it requires a ventilation capacity that consumes nearly 50 megawatts of power continuously. That is roughly the output of a small nuclear reactor. The electricity cost alone would add $4 per ton to the freight operating estimate, reducing the already thin margin to $14. So the tunnel exists in a state of permanent contradiction. It is technically possible, strategically desirable, and economically unviable. The Japanese government has not committed. The South Korean government has not committed, and the feasibility studies have been sitting in filing cabinets for 16 years. But every few years, a new proposal appears, and the media runs with it, because the idea of a tunnel connecting 2 ancient rivals is too compelling to ignore. What gets lost in the coverage is the reality of what it would take to dig the first shaft. The deepest shaft for the Seikan Tunnel was drilled through rock that reached 60 degrees Celsius at the face. The cooling system required pumping seawater through heat exchangers at a rate of 2 tons per second. The Korea Strait Tunnel would face temperatures that exceed 80 degrees at the maximum depth, because the geothermal gradient in that region is nearly double the global average. The rock is hot because the crust is thin, and the magma chamber beneath Kyushu is only 20 kilometers down. The miners would need active cooling suits and a refrigeration plant capable of removing the heat of 200 diesel engines operating continuously. That plant would need to be built on one of the artificial islands because there is no space on the mainland for that kind of infrastructure. And yet, the engineers who worked on the 2009 feasibility study are still convinced that the tunnel will eventually be built. Not in their lifetimes, but within the next 50 years. The reason they give is not economic or strategic. They talk about the 7 million ton rock crushing machine that would need to be designed from scratch because nothing in the existing inventory can handle the combined pressure, temperature, and hardness of the Korea Strait geology. They talk about the concrete lining that would need to resist chloride penetration for a century, which requires a formulation that has only been tested in laboratory conditions, never in an operational subsea tunnel. They talk about the failure modes that no one has simulated. And they talk about the cost of not building it, which is the cost of staying an island nation forever. The consortium's new proposal includes a provision for a pilot bore, a single tunnel of 4 kilometers that would test every system on a smaller scale before committing to the full crossing. That pilot bore would cost $1 billion and take 4 years to complete. It would answer the fundamental question that no study has resolved: whether the ground conditions are actually drillable. If the pilot bore succeeds, the full project receives a green light. If it fails, the entire concept is shelved for another generation. And the most recent engineering journals from Japan suggest that the consortium is already applying for the pilot bore permits through a private maritime construction company, bypassing the government approval process entirely. If the pilot bore goes ahead, the first 1,000 meters will decide everything. That section is the shallowest, the coolest, and the least tectonically active. It is also the section that will establish the baseline for every future decision. If the cutter head advances at less than 10 meters per day, the full tunnel will take 30 years, not 15. If the water inflow exceeds 50 liters per second, the freezing technique used in the Seiken will be too expensive to repeat at this scale. If the gasket tests show any creep whatsoever, the design life shrinks from 100 years to 50. Every variable is a hard schedule constraint. The most honest assessment comes from a retired chief engineer of the Japanese Railway Construction Agency, who told an industry conference in 2024 that the tunnel is not a construction project. It is a decision about whether Japan wants to remain an island. That decision has been deferred for over a century, and it will likely be deferred again. But the pilot bore changes the calculus, because a pilot bore is not a tunnel. It is a hedge, and Japan is a country that hedges against every risk, from earthquakes to energy supply to demographic collapse. The tunnel may be impossible, but the billion-dollar question is being asked seriously for the first time. When the first shaft is sunk into the seabed, whether it is next year or 20 years from now, the rock will be as hard as the studies predicted. The water will be as hot as the models forecast, and the cost will be as high as the skeptics warned. And someone will still turn the cutter head on, because the alternative is to accept a geography that refuses to change. That is the decision every deep project comes down to. You turn the cutter head on because you refuse to accept the ground as it is. If that refusal resonates with you, subscribe. This channel is built for the engineers who understand that the rock never negotiates. In the comments, write refusal. Tell us about a project where you refuse to accept the geology. They will turn it on because the physics of the strait is not a negotiation. You do not bargain with 80 megapascals of water pressure. You do not compromise with rock that sits at 60 degrees Celsius and folds under its own weight every few decades. The tunnel exists as an idea precisely because it refuses to accept that negotiation. If you have ever stood at the edge of a construction site and watched a 30-meter crane lift a section of steel into place, you understand the gap between a drawing and a structure. That gap is what the pilot bore is designed to measure. Not the geology, not the gaskets, not the cooling systems. The gap between what engineers believe they can do and what the rock will allow them to do. That gap is the only number that actually matters. The ground beneath the Korea Strait does not care about supply chain insurance. It does not care about the 50-year timeline or the 100-year design life. It does not care about the consortium's proposal or the feasibility studies in the filing cabinet. It simply is what it is. The rock, the heat, the fault lines, the pressure, and every engineering problem that the tunnel presents can be traced back to that single refusal to accommodate human ambition. The retired chief engineer, who spoke in 2024, said something else that day. He said that the tunnel is not a decision about construction at all. It is a decision about whether Japan accepts the territory it was given or insists on changing it. That is the quiet truth that no feasibility study includes in its executive summary. The tunnel is an act of refusal, a refusal of the sea, a refusal of the tectonic boundaries drawn by the Philippine sea plate's slow, relentless subduction, a refusal of the geography of islands. You will hear the cost estimates, and you will think the barrier is money. You will read about the gasket creep, and you will think the barrier is material science. You will see the temperature projections, and you will think the barrier is thermodynamic. But the barrier is older than any of those. It is the simple fact that the rock does not move for you. The deepest tunnels are not built through negotiation. They are built through exhaustion. So when the first cutterhead bites into the seabed off the coast of Kyushu, it will not be solving an engineering problem. It will be answering a question that Japan has been asking for 130 years. And the answer will be written not in yen or dollars, but in meters per day, in gasket compression, in the temperature of the water that flows through the cooling system. The answer will be the rock itself. And that is the only answer that has ever mattered.